In inequalities, we will be looking at expressions that are set not equal to one another, where they are set greater than or equal to, less than or equal to one another. And we'll be looking at how to express that in interval notation. So for the most part, we treat inequalities like we would equivalent equations. Therefore, adding or subtracting the same number on both sides does not change the solution. If I subtract 2 from both sides of this inequality, I will not change this inequality. Multiplying or dividing by the same positive number also does not change the solution. However, multiplying or dividing by the same negative number does change our solution. And what we need to do is we need to reverse the inequality sign. Let's take a look at why this rule is true. If we have a negative 2x is less than 4, our rule says when we divide by a negative 2, we reverse the inequality sign, having an answer of x is greater than a negative 2. Well, I can also use algebra to manipulate this. First, I'm going to subtract 4 on both sides. Then I'm going to add 2x to both sides. And now I'll divide by 2. Getting a negative 2 is less than x. And we can see that x is greater than a negative 2 is the same as a negative 2 is less than x. We can rewrite this as x's are greater than a negative 2. Notice the inequality sign always points towards the same item in that inequality. Using our properties of inequalities and our strategies for solving equations, we are going to isolate our x variable. Here you can see I started by distributing 3, getting 6x minus 27 is less than 9. I then add 27 to both sides and divide by 6, leaving me with an inequality of x is less than 6. And we are going to look at how to represent this in something called interval notation. Interval notation uses the idea of brackets and parentheses to help us understand what this interval is displaying. For example, if we look at x's are less than 6 on a number line, we can choose numbers that are less than 6, such as 3 or a negative 7. We can then shade all of the area that is less than 6. However, we are not equaling 6, so we are going to use parentheses to show that we are not going to equal 6, that we are less than. And notice how that parentheses opens up toward the way our inequality is pointing. Now, how do we put that into interval notation? Well, interval notation, if we think back to our line of x is less than 6, it shows us that x starts down here at a negative infinity. And because infinity will never have an end, we will always use a parentheses, because there's never a stopping point of infinity. So we then would write the interval notation as parentheses, a negative infinity, to parentheses 6, showing us that any number between negative infinity and 6, but not including 6, is a solution. Looking at x's are greater than or equal to 12. Again, we can plot points, recognizing that any number greater than 12, but also equal to 12, is a solution, which is why we will use a bracket in this instance. And be careful on this last one. We're looking at a negative 5 is less than x, which can also be rewritten as x's are greater than a -5. Either way, we need to choose points that make sense with our inequality. So 0 is greater than a -5, or -5 is less than 0. So we know we are going to be shading towards positive infinity, but not including a -5. So we will be using a parentheses in our interval notation. Now to solving inequalities. In having -12x minus 8 is less than or equal to 16, I first need to solve this. I'm going to graph it on a line to help me display my interval notation. I want to isolate x. I'm going to start by adding 8 to both sides. So a -12x is less than or equal to 24. I'm then going to divide by a -12, remembering my rule that when dividing by a negative, you must reverse the inequality sign. And so I have x's are greater than or equal to a -2. Looking at this on a number line, I'm looking for numbers greater than a -2 and equal to a -2. So I'll be using a bracket, -2 to positive infinity, parentheses. We can also look at compound inequalities, where we'll be looking for the union or the intersection of these intervals. For example, if we're looking at x's are less than a -4 and x's are greater than a -7, I would begin by graphing. In this graph, I'm going to start by looking at x's are less than a -4. So I know because it's less than a -4, I want a parentheses. I'm going to be working my way less than that. Now, in green, I'm going to show x's are greater than a -7. I again have a parentheses because I'm not equal to it, and I'm going to be moving greater than a -7. And where the and, where both things occur, are where we see both shaded lines, or both colors of the line. So we can see that between -7 to -4, and not including those numbers, is where there is an intersection or an and of these two intervals. We can do the same thing looking at x's are greater than or equal to a -1, or x's are less than or equal to a -3. And or is denoted by the union symbol. So with x's are greater than a -1, and equal to it, I'm going to have a bracket shaded toward positive infinity. It says, or x's are less than a -3. Again, I'm going to use a bracket at -3 and shade down to -infinity. Now we are looking where one or the other occurs. So we are looking where any part of the shaded line occurs, meaning my interval notation would say start from the left here at -infinity, move up to -3 and include that, or I'm going to use my union symbol, start at -1 and include it, and move up to positive infinity. In interval notation, then, we need to graph these items to help us. So, solving these two inequalities, I'm always going to be looking to isolate x. I'm going to start by subtracting x on both sides. Getting 3 is less than or equal to x minus 1. Adding 1 to both sides, I have 4 is less than or equal to x, or rewriting that as x is greater than or equal to 4. solving my second inequality expression, I'm again looking to isolate x. I'm going to start by subtracting 5x to both sides, getting a negative 2x minus 2 is less than a negative 4. Adding 2 to both sides, I have a negative 2x is less than a negative 2. Dividing by a negative 2 on both sides, I have to remember to reverse the inequality, finding out that x's are greater than 1. Now, looking at this on a number line, x's are greater than or equal to 4. I'm going to have a bracket shading towards positive infinity. With x's greater than 1, I'm going to have a parentheses, again shading towards positive infinity. And I'm looking at the intersection of where these two things occur. So again, where do they both occur is where both items are shaded, and that would be at 4, moving towards positive infinity. Lastly, we want to look at double inequalities. This is an and inequality where we can see that a negative 3 is less than or equal to 2x plus 5, and 2x plus 5 is less than 7. To solve this, though, we can treat this inequality by isolating the x in the center and applying the properties of inequalities to all three parts. So to do this, by isolating x, I am going to subtract 5 to the middle, to the left, and the right-hand side. Leaving me a negative 8 is less than 2x, less than or equal to 2x, which is less than 2. I'm now going to divide all three parts by 2, getting a negative 4 is less than or equal to x, which is less than 1. And because this is an and, I know I am looking for where these things intersect. Splitting this apart, I could see that negative 4 is less than or equal to x, or I could rewrite that as x is greater than or equal to negative 4. I'm also seeing that x is less than 1, and I can see that both items are shaded between a negative 4 and 1. So I'm moving, including negative 4, to positive 1.